morning, everybody. It is our great pleasure to have Professor Mitsuru Kikuchi here. Mitsuru is a well-known scientist in the field of nuclear fusion. He's a supreme researcher in the Japan Atomic Energy Agency. Also, he's a member of many advisory committees in the world for nuclear fusion and related science. It's a great pleasure, that also great honor that we could have him as our visiting professor since last year. So he has been giving intensive course almost every day for 2 weeks per year about plasma physics. This time also he stayed here with us for this purpose. And today he's going to give us a more general talk about the plasma physics, the frontier of the science of matter. So let's welcome.
So thank you very much, Yamin. And I'm very pleased to come here to give a general talk on plasma physics. And I'm working on fusion research. However, I have more, because I'm now a senior in JAEA as a supreme researcher. I'm expanding my field to many other plasma physics related fields. And today I'm giving a talk on general plasma physics, which has been prepared for the plenary talk at the conference in Malaysia for the general physics, including a lot of intensive talk on Higgs particles. And especially I thank to Yamin and also FUDAN, T.S. Han, Idomura, Ru Chen, and Frank Chen, and Professor Shibata and Tsuneta, Tajima and Mahajan, and Kikuchi. And so, before my talk, I'd like to talk about the relationship to FUDAN. Yamin kindly invited me to come to give a talk in 2010, I think. And we had a good discussion on the fusion research in FUDAN. After that, when I became the visiting professor in FUDAN to give a talk in last year, so around that time, I visited many places like Max Planck and Chengdu, FUDAN, and USDC, and Asian School in Jeju, and ICTP, International Center for Theoretical Physics, Trieste, University of Tokyo, Nuclear Fusion Board of Directors, Fusion Energy Conference, WCI in Seoul, Tsinghua, Peking, and USDOE and USTTF in California, and the Zhejiang Universities and INEST, Nuclear Safety Institute, and USTC again, and ASIPP, SMTTF, European Physical Society in Espoo, and the APPC in Makuhari, and Malaysia, IFSA, and Chengdu, and the University of Tokyo. So these days I'm traveling around to have more lectures and talks on plasma physics. Especially in these days, Asia is quite hot in fusion research. And the invited lecture in China, Korea, and Japan, I give a lot of places in China and Korea and Japan. So you can see from there that how much activities are going on China as well. And my talk is as follows, and starting from a Nobel Prize in Physics in 2013, and because this year Professor Higgs will receive the Nobel Prize in Physics, and then that I'm going to talk about the plasma physics and the introduction. And main topics will be advances in plasma physics in the area of topology, equilibrium, gyrochrono theory, self-organized criticalities, and self-generated currents, and the spectrum, and wave particle interactions, and dynamo, flares, and substorms, and relativity in plasma wake field acceleration and cosmology, and finally the plasma technology. So this is a kind of a tutorial collections on plasma physics, mainly from the contribution from APPC plasma physics, which I organized the meeting, and also coming from my Springer book on frontier inclusion research, and also on review modern physics, and published in last December. As you know, the review modern physics is a high impact factor journal, having impact factor something like 4 to 3.9, which is much higher than the Nature or Science, and as well as physical review letters. And most of the leading physicists in all physics area is writing this review papers during the last career of his career. Okay. So anyway, this year, Nobel Prize in Physics 2013 is announced quite recently to be given to the theoretical discovery of Higgs particles, like to Peter Higgs and Francois Englert. These are published in PRLs in early days, in 1964 or something like that. And in this year, in Malaysia, in August, we had an interesting international physics conference. It is called the 4th International Meeting on Frontier of Physics. Has been held in Malaysia. And here is a person coming from LHC. LHC is located in Ceylon to have experiments on discovering the Higgs particle. This is Professor Landsberg, who is LHC. CMS, there are two detector systems. One is CMS, one is Atlas. And Professor Landsberg is leader on physics coordinator of CMS facilities, and from Brown universities, and also LHC Atlas leader is Professor Christos. He's quite young guy, and coming from Edinburgh University. As you know, Professor Higgs was the professor in Edinburgh Universities. I'm here as one of the plenary speakers of this conference on plasma physics. And this is the Professor Landsberg talk during this conference. He is so much excited to raise his hands to talk about what is the Higgs mechanism. And what was the excitement during the experiment to observe the Higgs particle. So this Higgs particle is named by the Leon Lederman as God particles. Okay? And what is the original mass is explained by the Higgs particles. And he explained to us very enthusiastically on the origin, how they discovered the Higgs particle during this conference. This has been given that, as you know, that in all physics area, we always use Lagrangian for the particle physics and also plasma physics. And this is kind of Lagrangian for the kind of Ginzburg-Landau form, which has been first discussed by the Landau and Ginzburg on the superconductivity. And since it has kind of bell-shaped, heart-shaped, inverse heart-shaped structure of the potential surface, this freedom, radial freedom, means there is some difference in energy. That means we have a mass difference. So this is the freedom for the Higgs particle having mass, and this freedom, there is no change in energy or mass. That means it corresponds to the photon. So that the Greg kindly introduced the Higgs particles and difference in Higgs particle and photons by using this Ginsburg random potentials. That was very interesting. And also, plasma physics, there is 12th Asian physics conference has been held in July, including the Nobel laureate Makoto Kobayashi, who finalized the standard theory on the elementary particle physics. And also we had many plasma physics speakers in this conference. The total participant of the Asian Physics Conference was 1,290s. And among them, we have plasma physicists, something like more than 300 people. So that means that the plasma physics field becomes a measure of the physics field, playing 1/4 of the peoples in this Asian General Physics Conference is coming from plasma physics area. This is because I made a strong effort to invite many people to have good talks, and many people are interested to come, including Lui Chen and Tajima and Shibata and Pikachu. So these are the photos during this conference, which I managed to have more people to come. So I'd like to start from my talk on the introduction to plasma. So plasma is a kind of fourth state of matter, as you know. We have solid and liquid and gas, and then plasma. On our planet Earth, the most of the matters are solid or liquid or gas. However, outside our planet, it is mostly a plasma. Most of the materials, visible matter, is said to be plasma. So typical example, our sun, right? Sun is a huge mass of the plasma, right? So this is our planet Earth, and you can see how big is the size of the sun. So to understand the behavior of the sun, you have to understand the plasma physics. That is inevitable, right? And also from the sun, we have a solar wind is coming, and we have magnetosphere, which is formed by the Earth's geomagnetism. And to understand the geomagnetism, you have to also learn a lot on plasma physics. Okay. So now we fusion communities are intending to bring the sun on the Earth. It's called ITER. Okay. So ITER, but the ITER site is something like a building in the Washington D.C. So it's big, huge machine, and cost quite a lot of money. And participants are including China and India, so Japan and Europe and the United States and Russia and Korea. That means more than 50% of the population is now joining this fusion program. So that is a huge, big project. So there are 3 kinds of huge, big science projects, like a space station, an accelerator program, and then fusion. These are 3 big scientific programs. So that if you understand plasma or plasma physics, take the plasma physics course, you can have many opportunity to have to join to this one of 3 big scientific projects. That is the situation. Okay? And also, plasma has a very interesting feature, like so-called plasma wave field acceleration. This has been first understood by the Professor Tajima, and to have a very, very efficient particle acceleration mechanism. And most of the accelerator people working on the elemental particle physics are quite interested in this physics mechanism. And also, in order to understand early universe generation of the magnetic field, there are some relativistic theory on the plasma physics which can explain the origin of the magnetic field generation in our universe, explained by the plasma physics as well. So that is the general view of the plasma physics expanding in these days. And I am specialized to fusion research, so that the fusion has a long history of research, starting from more than 50 years ago. In 1958, you see in Geneva, there is some United Nations branch in Geneva. In the center, you see Professor Yukawa, who is the first Nobel laureate in Japan, and for the theoretical discovery of the method. And then 20 years later, we had the 22nd Fusion Energy Conference. And I am here, and I don't know whether you can see it, because I am the chairman of the International Program Committee of this conference, anniversary conference. I'm in the front, and this is a symbol of the United Nations. So fusion is a very, very challenging project to bring the sun on the earth. And to do it, we need a huge, huge effort to understand particle physics, and also atomic and molecular physics and plasma interaction. And then we are now constructing a huge machine called ITER. You see, this is the size of the man, this is the size of the cathode views, other view of the ITER machine. And here you can see the site of the main building. And we have a huge negotiation process for the ITER construction, and spending many monies in this site. Okay. However, China, in these days, this is a major radius. We will have a torus like this, and this is the size of ITER. And we in Japan, between Europe and Japan, we are constructing a new superconducting tokamak called JD6DSA. And here you can see the Korean superconducting tokamak called K-star, Korean stars, right? And in Hopei, you have East tokamak, and it's also superconducting, but the plasma current is 1 megampere, and while the ITER is 15 megampere, and Japan's tokamak is 5.5 megampere plasma current. And India, they have a very, very small tokamak called SSP. So the academician Yuan Kiwan, the dean of the School of Nuclear Science and Technology, is a leader to make China to make a more major contribution fusion research, to have next step device, CFETR, and to have a fusion power. It's actually burning the plasma, and to prove the fusion energy cycle, and the size much bigger than the Japanese one, and to burn the deuterium-tritium. The most likely candidate is located in the Shandong province, home of that guy, and it's close to Korea as well, and Japan as well. So this project will be a big challenge for China to make the major contribution to the fusion research. And I'm quite supportive to promote this kind of big project in China, because China is number 2 countries. The GDP of China surpassed Japan, and EU becomes the number 2 in the world after United States. So why not? That is the present status of the China. You have big power and many peoples, very good peoples here. So to do that, you have to understand plasma physics, and plasma physics becomes a fundamental discipline for many, many fields, like magnetic confinement fusion, cosmology, astrophysics, solar physics, space physics, earth physics, and also many, many applications of the plasma coating for semiconductor, nano, bio, and medicine, and also space engineering for space propulsion, for accelerator, and radar physics. So for these various fields, you need to understand the basic plasma physics. That is for sure. And unfortunately, there is no strong activities in FUDAN, this university in FUDAN, and to have a strong activity on plasma physics. That is a pity, and that is, we share our concern with Yamin. Okay. So I'm going to talk about the advances in plasma physics, starting from topology. You can see from my Springer. And the sun is a natural fusion reactor. Okay? Sun is a natural fusion reactor, having the topology of a sphere. And this, because, why it is a sphere? It is because the force, gravitational force, has a vector field. In the force acting along this field line. Because of this, the topology becomes a sphere. But in the case of magnetic confinement fusion, it is the J cross B force. That means the force acting perpendicular to the magnetic field. And because of that, the topology of the magnetic confinement fusion becomes a torus. Okay. And the Andy Poincaré is the first person to prove the so-called Poincaré theorem that closed surface that can be covered with a non-zero vector field is limited to the torus. So you can see the torus can be covered with non-zero vector field, but on the other hand, sphere cannot. So this is a very important topological characteristic of the vector field. And also for magnetic confinement fusion or for magnetic flux topology, you see a lot of interesting papers from Review Modern Physics and Nature, Moffat, that kind of things. And then that I'm going to talk about equilibrium in plasma. So we know that the plasma in magnetic confinement fusion is confined by the J cross B force to balance against the pressure force. So that means these Grad and Sharpov find the so-called Grad-Sharpov equation for the magnetic confinement fusion. This we are solving daily for tokamak systems. And this also can be applied to the magnet sphere equilibrium applied by the Professor Frank Chen in Taiwan as well. And the interesting thing is the confinement geometry. We see lots of development in what is the structure of the magnetic field. This guy is my friend, and he's a director general, Osamu Motojima, who was former director of the National Institute of Fusion Science. And he told to all the physicists, researchers, especially in NIFS, they are promoting the helically wounded confinement system called helical systems. Helical researchers must see complicated magnetic field line as a straight field line. If he can see this complex dragon-shaped magnetic field line as if it is a straight field line, he becomes a scientist. That's his word. But mathematically, it is true that there is some coordinate transformation who can see that magnetic field line becomes a straight field line that is called flux coordinate. So that is an interesting coincidence between his work and plasma physics. So then another interesting development is the so-called dialectic theory, which is written in very modern physics and to these early days. And first, this is a professor in US University of California, Robert Littlejohn, who find that for the guiding center, we have, for the charged particle motion in the magnetic field, we have a gyro motion and slow drift motion. And then for the slow drift motion, the Nobel laureate Hans Alfvén derived so-called guiding center equation of motion. However, his equation of motion doesn't satisfy the Liouville theorem in the classical mechanics. And he was the first person who understood, well, we have to change the guiding center equation. And the only way to satisfy the Liouville theorem is to use the Lagrangian. If we use Lagrangians throughout the mathematics, we can always conserve Liouville theorem, or space volume is conserved during the motion. That was the most important development for the particle simulation of the plasma turbulence. And then Professor T.S. Hahn in Seoul National, now is in Seoul National Universities, understood that if we have a fluctuation, a turbulent fluctuation with the wavelengths close to the gyro motion, there will be a breakdown of magnetic moment. Mu is not conserved quantities. And then he applied the so-called Lie transform technique to the plasma physics to see, to convert Lagrangian differential one form to invariant to the gyro motion, gyro phase. And this was very successful to achieve gyro phase independent Lagrangian differential one form for the plasma particle motion and the turbulent fluctuation. That was a very major development, and then we now have a very, very sophisticated supercomputer code system called Gyrokine Brother-Poisson equation in 5-dimensional space, including velocity space and real space. And say, for example, our staff, Idomura, is solving this gyrocantic Brother-Maxwell equation using a K supercomputer, which was the #1 in the world in the past. So, and solving and discovered there are a lot of interesting physics for the turbulent transport in plasma physics. Then, important another development in plasma physics is so-called self-organized criticalities. As you know, that Prigogine was the first person to notice the non-equilibrium statistical physics, or this also self-organized criticality. So self-organized criticality is the system will become critical by itself. Talking about the sun collapse in the sun pipe, you see the system stays at critical state, like similar to the avalanche dynamics, and also even the earthquake dynamics follows this critical phenomenon. And there is a big similarity with gyrotonic simulation for the self-organized criticalities. Okay. And to explain the physics in the self-organized critical transport in plasma physics, Pat Diamond and T.S. Hahn made wrote an interesting paper in POP to clarify the avalanche dynamics of the void and bound, and to explain the turbulent transport. And also, there is but not only this, we have another structure for the turbulent transport physics, include so-called zonal flow physics to regulate turbulence itself. So he found that the turbulence, if we have a plasma profile, this profile has a free energy to drive the microturbulence. The old paradigm was this microturbulence will regulate the pressure profile. However, now we understand there are another important mechanism, that is flow. So the turbulence can produce the flow, so-called zonal flow, you see in Jupiter. And then this zonal flow can also regulate plasma turbulence. And then these three processes as a new paradigm for the plasma turbulent transport. That was the recent finding. He wrote some review papers in plasma physics and controlled physics. And for that reason, we have some change in the critical self-organized critical transport in plasma physics. That you need more physics understanding there. And now I'm going to the next interesting physics topics, plasma physics, so-called self-generated current. I have two examples. One is a very, very well-known, famous dynamo current. We have geomagnetism, which is produced by the rotation of our Earth itself. The physical explanation of the why we have geomagnetism is based on the dynamo theory. So interestingly, we have another mechanism to have a self-generated current, so-called bootstrap current. Actually, my major is on bootstrap current. I wrote review papers on this bootstrap current by the request of the European Physical Society. And also, this review modern physics is mainly talking about the bootstrap current observation. So, the self-generated current has been predicted by the Roy Bickerton and also Zagde in early days. The tokamak uses the transformer action to drive the plasma current as a confinement field. However, if we have plasma pressure, then in collisionless regime, plasma itself can generate plasma current, which is called bootstrap current. And the mechanism behind the generation of bootstrap current, you have to read my Springer book or Chinese edition of my book. And it takes more time to explain what is the mechanism. That there is an interest in physics here. And we now see the bootstrap current should be proportional to the normalized pressure. And we now have even up to 80% of the plasma current carried by the self-generated plasma current called bootstrap current. also we see quite recently measurement and theoretical calculation agreed quite well on the existence of bootstrap current, which is a collisionless current during the plasma pressure itself. And another important self-change current mechanism is dynamo action. In our planet Earth, we have geomagnetism. This is coming from the outer core of our Earth. Because of the rotation, of our Earth, we have, in the outer core, it is a liquid metal, as you know, okay? This rotation, because of the Taylor-Proudhon theory, we have Taylor-Proudhon crown, and you have convectives, small convectives there. And due to the Ekman pumping mechanism, we have generation of magnetic field. That has been discovered theoretically from the numerical simulation of the electromagnetic fluid simulation, 3-dimensional, by the Kageyama. He also published a Nature article on this. Okay. Another interesting development for plasma physics is spectrum and Alphen eigenvalue. As you know, in quantum mechanics, you learn quantum mechanics, and you see discrete spectrum inside the confined quantum potential, but in free space, you have a continuous spectrum because there is no boundary condition. Similarly, we have a kind of continuous and discrete spectrum in plasma physics. So a typical example to have a continuous spectrum is this kind of equation as a solution as a function, as a delta function. And this lambda eigenvalues can be arbitrary because there is no boundary condition. And this is, we call a continuous spectrum. It's coming from the non-square integral function. And there are two types of continuous spectrum. One is so-called random damping, coming from in velocity space continuous spectrum, and also Alphen continuous spectrum due to the spatial uniformity produces a continuous spectrum in plasma physics. That is published by Hasegawa and Chen in PRL. And he is now in Zhejiang University and as a director of the Center for Fusion Theory. And very interestingly, we have in plasma physics, if we have a toroidal plasma, we have a kind of good similarity with solid-state physics. In solid-state physics, if we have a lattice structure and infinity, like here, the spectrum shape depends on the distance of the interparticle distance. If we have an interparticle distance because infinity, it becomes a point spectrum for this system. And then, if the interparticle distance becomes shorter and shorter, it becomes a continuous spectrum. And close to the free electron conduction region, we have infinity discrete spectrum. That is the situation for semiconductors, right? Quite similarly, in plasma physics, in toroidal system, we have a spectrum for the shear alpha wave, and the two alpha waves can couple each other to have a gap structure right here in solid state physics. And inside the gap, we have a point spectrum inside. And this is called toroidal alpha eigenvalue, which can be very, very dangerous for the alpha particle to be disturbed by this alpha eigenvalue. And Frank Chen was the first person to notice the importance of this point spectrum inside the gap. Very, very similar to the point spectrum in the solid state physics. And Louis Chen is the world leader in this alpha eigenvalue physics. And he is now writing his own debut modern physics paper to be published very soon. Okay? And then